Hello, Assalamu alaikum. This is Abdullah. And in this video, I'm going to be explaining two examples about the DC power supply. And I want to apologize in advance if I take a break in between or I cough and due to my bad voice. And I hope that you would excuse that. So, beginning with the first example, we have example 2.12, in which we have been provided a parallel diode configuration that we have to determine V out, I1, ID1, and ID2. So, we have a 10 volts battery and a 0.33 kilo ohms resistor, and we have two diodes connected in parallel. So, this means that the same current would be flowing across these diodes. So, we can find this current by using Ohm's law, which is V is equal to IR. Also, we would subtract the total current, which would be, oh, sorry, the total voltage, which would be 10 volts from the voltage of that would be used by the diodes respectively. This voltage would be 0.7 volts in case of a silicon diode. So we would use 10 minus 0.7 volts divided by 0.33 kilo ohms. This will give us 28.18 milliamperes. And assuming the diodes are of similar characteristics, we have ID1 is equal to ID2. So we would divide I1 by 2, we would get 28.18 milliamperes divided by 2. The answer would be 14.09 milliamperes. This means the 14.09 milliamperes current would be passing through each diode. Okay, so we can see the Proteus simulation for this. So in Proteus, we have used a 10 volt battery. I have used a single cell battery because it looks similar to which we have what we have been provided in the slides and the books. A 0.33 kilo ohms resistor, a voltmeter, and 2 millimeters. Millimeters to use current, voltmeter to use voltage. Because so to measure voltage, I have attached one voltmeter across one diode and one ammeter across another diode because the same current and voltage will be flowing through them. So there's no point to attach separate for each one. And this would measure the total voltage, the total current. So the simulation would result in this, and we can compare these values. These are the exact same values which we had been shown here. These values 28.18 milliampere at 14.09 milliampere, which would be 14.1 milliampere. So now going to the next example, which is provided on slide number 48, I believe. Okay, so in this example, we have been provided a zero voltage regulator, and we have to find V zero, VR, and I zero and R load for a 3 kilo ohms resistor. First, we would find the voltage by a simple method, which is a voltage division rule, in which we would use the load resistance divided by uh, this resistance plus the 1 kilo ohms resistor multiplied by total voltage would be 16 volts. So this would result in 12 volts. So in a zero voltage regulator, it requires more current than it is mentioned on it for current to allow to flow through it. Like 10 volts is mentioned here, so and 12 volt is given. This means that this would allow current to flow through it. Now V is greater than VZ either is on, and VL becomes equal to VZ is equal to 10. So the zero voltage diode regulator becomes on, and it would allow 10 volts current to flow through it. VR is equal to VI minus VL, which is 16 minus 10 is equal to. So V resistor is equal to total current subtracting the current flowing across the diode, which would now result in 6 volts. So I load will be calculated easily because we have V load and R load. Now this would result in 10 volts divided by 3 kilo ohms, and which will be equal to 3.33 milliamperes. And the IR, which is the current across the resistor, would be equal to VR divided by R, which would result in 6 divided by 1 kilo ohms, which is equal to 6 milliamperes, and I zero is equal to 2.67 milliamperes. Also, we have calculated the power. The formula for calculating power is P is equal to VI. In this case, the 10 volt multiplied by 2.67 milliampere is equal to 26.7 millivolts. The Proteus simulation for this is the Proteus design is like this, in which a 16-volt single cell battery is used. Millimeters and voltmeters are used to measure current and voltages respectively, and 1 kilo ohm resistor and a Zener diode, which can be found in the library by typing 1N4740A, and a 3 kilo ohms load resistor. So let's see what results it will give after simulating. It shows 6 milliamperes current, almost 6 milliamperes, 6 volts voltage, 10 volts voltage across a Zener diode, and 2.66 milliampere current across the Zener diode, and also 3.34 milliamperes current across the load resistor, and the same voltage would flow across these two because both are in parallel configuration. So we can compare these values and we would see that these are the exact same values. Now, going on, we are going to discuss about the DC power supply. So what is a DC power supply? A direct current DC power supply is a device that converts alternating current AC to direct current DC, or from one voltage to another. Most electronic devices and circuits are provided by a DC power supply. The majority of DC power supplies are in the form of wall adapters, which are used in our homes. So a DC power supply's configuration is like this, and this, as we can see, we would also be using rectifier diodes. These rectifier diodes, and this is a full wave bridge rectifier, which will be discussed below. Uh, this is a capacitor that would cause ripples like this in oscilloscope where we connect it to find the wave. And this is a data sheet for the diode. The data sheets are used to measure the maximum voltage and current that can be uh, like uh, the maximum amount of current that could go through a diode is and the maximum amount of voltage that a diode can bear are mentioned on the data sheet, and it is necessary to learn how to read a data sheet. While creating the PCB for a DC generator, it would look a bit like this, and for a wave, we would connect oscilloscope like this, and uh, the probes to the PCB like this. So basically for us to get a good DC supply out of AC, it should have the least repulsions. Uh, we will get pulse voltages when we use a bridge rectifier, but for pure DC, a pure DC is like almost like a straight line, and it is necessary for it to have the minimum amount of vibrations in it. uh, Now, the forward bias and reverse bias are discussed here. The forward bias permits more majority carrier current, and reverse bias prevents majority carrier current. So there is a difference between permits and prevents. Also, we can see the bias voltage connections. Positive anode A is first, and negative anode K is second. The bias voltage must be greater than the barrier potential. Barrier potential is the potential that is used by the diode to like work, which is 0.7 volts for silicon. The majority carrier provides the forward current. The depletion region narrows, and the bias voltage must be less than the breakdown voltage. There are no majority carriers after transition time, and majority carriers provide a negligible small reverse current, and depletion region widens, and bias voltage connections are positive to cathode and negative to anode for the reverse biased configuration. S- Now discussing a half wave and a full wave rectifier. Basically, a full wave rectifier would be preferred by anyone because there are no missings in the full wave rectifier, and the wave is constant like this. As we can see, the output voltage waveform is consistent. while in the half wave rectifier the output waveform would not have the negative values, and it would be empty like this. It would only have the half positive wave. But in the full wave, the half positive wave will also behave like the half negative wave will also behave like a half positive wave, and we would get constant pulsating DC. The formulas for a half wave rectifier for uh, peak output is voltage of peak secondary voltage minus 0.7 volts. In case of a practical diode, we have to subtract the 0.7 voltage out of the calculations, but in ideal diode, there is no need to subtract 0.7 volts. Average voltage, average value of output V average is equal to V peak output divided by pi for average, and diode peak inverse voltage is the same for is the same as peak secondary current. In case of practical diode, we have to minus or subtract 0.7 volt. The peak value of output is Vp out is equal to Vp secondary divided by 2 minus 0.7 for a full wave rectifier, and average output value is 2 V peak output divided by 5. A diode peak inverse voltage is equal to 2 V peak output plus 0.7 volts. A bridge full wave rectifier peak value of output V peak output is equal to V peak secondary minus 1.4 for a full wave rectifier, because two similar type of diodes would add up, and 0.7 plus 0.7 would give us 1.4 volts, and average value of output would be V average equal to 2 VVP output divided by pi. And a diode peak inverse voltage PIV is equal to VP peak output plus 0.7 volts. So this was the explanation, a bit of explanation which I could do about examples and DC power supplies. Thank you.